Certainly, a nuclear fusion reactor aims to replicate the process that powers the stars, including our Sun. Here's a detailed explanation of how it works. Principle of fusion. Nuclear fusion involves combining light atomic nuclei to form heavier ones, a process that releases a tremendous amount of energy. The most common fusion reaction in research is between two hydrogen isotopes, deuterium D and tritium T. When these nuclei fuse, they form helium and a neutron, releasing energy according to Einstein's mass-energy equivalence, E equals mc²2 Key components of a fusion reactor. Fuel. The fuel for a fusion reactor is typically a mix of deuterium and tritium. Plasma. The fuel is heated to extremely high temperatures, forming a plasma, which is a hot, ionized gas where the electrons are separated from their nuclei. Magnetic confinement. Fusion. Magnetic confinement. To contain and control the plasma, magnetic fields are used, often in a device called a tokamak. The magnetic fields act as a magnetic bottle, preventing the plasma from touching the reactor walls too. Conditions for fusion. For fusion to occur, the plasma must be at a high temperature, over 100 million degrees Celsius, high pressure, and sufficiently dense. These conditions ensure that the nuclei have enough energy to overcome their natural electrostatic repulsion, known as the Coulomb barrier 3. Energy generation. Once the conditions are right, the deuterium and tritium nuclei can collide and fuse. This fusion process releases a neutron and a helium nucleus, alpha particle. The neutron carries away much of the energy as kinetic energy, which can then be absorbed by the reactor walls, heating a coolant. This heat is then used to produce steam and drive turbines to generate electricity. Challenges. The main challenge with nuclear fusion is achieving a net energy gain, that is, getting more energy out of the reaction than is put in to sustain it. The plasma must be confined for a sufficient time and at high enough temperatures to allow for a significant number of fusion reactions. 5. Safety and waste. Fusion reactors are considered safer than fission reactors because they don't rely on a chain reaction, so there's no risk of a meltdown. Additionally, they produce less radioactive waste, and the waste they do produce has a shorter half-life. 1. Current research projects like ITER, International Thermonuclear Experimental Reactor, are under construction to demonstrate the feasibility of fusion power. ITER aims to produce a Q-factor ratio of fusion power to input power of 10, meaning it would generate 10 times the energy required to maintain the plasma. 1. In summary, nuclear fusion reactors work by heating and confining a plasma of hydrogen isotopes until they fuse into helium, releasing energy. While the technology holds the promise of a clean and abundant energy source, significant technical hurdles remain before it can be commercially viable. The ongoing research and development aim to overcome these challenges and harness fusion as a sustainable energy source for the future. Nuclear fusion and fission are two different nuclear processes that release energy, but they operate on opposite principles. Here's a detailed comparison. Nuclear fission process. Fission occurs when a large, unstable nucleus, like uranium-235, is split into two smaller nuclei, along with additional neutrons and a large amount of energy. 1. Chain reaction. The additional neutrons released can initiate further fission reactions, creating a chain reaction. 1. Energy release. Each fission event releases a significant amount of energy, primarily in the form of kinetic energy of the fission products. 2. Applications. Fission is the process used in nuclear power plants and atomic bombs. 2. Waste. Fission produces radioactive waste that requires long-term management. 1. Nuclear fusion process. Fusion occurs when two light nuclei, typically isotopes of hydrogen, combine to form a heavier nucleus, such as helium, releasing energy in the process. 1. High requirements. Fusion requires extremely high temperatures and pressures to overcome the electrostatic repulsion between the positively charged nuclei. 3. Energy release. The energy released by fusion is several times greater than the energy released by fission. 2. Applications. Fusion is the process that powers the Sun and other stars. 3. It is being researched for use in fusion reactors, like ITER. 1. Waste. Fusion produces minimal radioactive waste, and the waste it does produce has a shorter half-life. 1. In summary, fission splits heavy atoms into lighter ones, while fusion combines light atoms into heavier ones. Fusion has the potential to be a cleaner and more abundant source of energy, but it is currently more challenging to achieve and sustain than fission. The Tokamak and the Stellarator are both devices designed to confine plasma for nuclear fusion, but they use different methods to achieve this. Tokamak, magnetic fields. It uses a combination of two magnetic fields to confine plasma, a toroidal field created by external coils and a poloidal field generated by an electric current that runs through the plasma itself. 1. Plasma shape. The plasma in a tokamak is usually donut-shaped, toroidal, and requires a continuous electrical current to maintain the confinement. 1. Operation. Tokamaks are more common and have been researched more extensively. They can potentially reach higher plasma pressures and, thus, better fusion conditions. 2. Challenges. They are prone to disrupt ions and require complex systems to control the plasma current and maintain stability. 2. Stellarator. Magnetic fields. A stellarator also uses magnetic fields to confine plasma, but it achieves the necessary twisted field configuration solely through the shape of its external coils, without relying on a current running through the plasma. 1. Plasma shape. The plasma shape in a stellarator is more complex and typically non-toroidal. 2. Operation. Stellarators are inherently more stable than tokamaks because they do not rely on a plasma current, which can cause disrupt ions. 3. Challenges. The complex coil shapes make stellarators more difficult and expensive to build. However, recent advances, like those in the Wendelstein 7X stellarator, show promise for the technology too. In essence, the main difference lies in how they create the magnetic confinement. Tokamaks induce a current within the plasma, while stellarators use a complex external coil design to produce the necessary magnetic fields. Each has its own set of advantages and challenges in the pursuit of sustainable nuclear fusion energy. Plasma behavior in a magnetic field is a fascinating and complex subject. Here's a detailed explanation tailored to your interests in physics and technology. Fundamental behavior. Plasma, being composed of charged particles, ions and electrons, is highly responsive to magnetic fields. The charged particles experience a force perpendicular to both their velocity and the magnetic field direction, known as the Lorentz force. This force causes the particles to spiral around the magnetic field lines. 1. Confinement. In the context of nuclear fusion reactors, magnetic fields are used to confine plasma. The magnetic field creates a magnetic bottle that constrains the motion of the charged particles, preventing them from coming into contact with the reactor walls, which would cool the plasma and disrupt the fusion process. 2. Gyroradius and gyrofrequency. The radius of the spiral path, gyroradius, and the rate of rotation around the field line, gyrofrequency, depend on the particle's mass, charge, velocity, and the strength of the magnetic field. Electrons, being lighter, have a smaller gyroradius and higher gyrofrequency compared to ions. 1. Drifts and currents. Various drifts can occur in a plasma under a magnetic field. For example, if there's a gradient in the magnetic field strength, particles experience a drift perpendicular to both the field gradient and the field lines. Similarly, if there's an electric field, it can cause an /math E /times math B drift, where all charged particles move in the same direction regardless of their charge. 1. Instabilities. Plasma can also exhibit various instabilities in a magnetic field, which can lead to changes in plasma density, pressure, and magnetic field configuration. These instabilities are crucial for understanding phenomena like magnetic reconnection, which is important in both astrophysical contexts and fusion research. 1. Fusion research. In fusion reactors like tokamaks and stellarators, controlling plasma behavior in a magnetic field is essential. Researchers study how to optimize magnetic confinement to maintain high temperatures and densities necessary for fusion reactions to occur efficiently. 1. In summary, plasma in a magnetic field exhibits complex behavior that is central to many natural phenomena and practical applications, especially in the pursuit of controlled nuclear fusion. Understanding and controlling this behavior is one of the key challenges in developing fusion as a viable energy source. Plasmas, the fourth state of matter, have a wide range of applications in technology due to their unique properties. Here are some notable uses. Electronics manufacturing. Plasma etching, used to create intricate patterns on semiconductors. 1. Coating deposition, applies thin films on electronic components. 1. Material processing, cutting and welding, plasma torches provide high temperatures for metalwork. 1. Surface treatment, increases adhesion for painting or bonding. 2. Medical applications. Sterilization, plasma can sterilize medical tools without heat. 1. Cauterization, used in surgeries to minimize bleeding. 1. Environmental and safety, air and water purification, plasmas can break down pollutants. 3. Food safety, deactivates pathogens on food surfaces. 3. Aerospace, rocket propulsion, ion thrusters use plasma for propulsion in space. 1. Consumer products, lighting, fluorescent lamps and neon signs use plasma to emit light. 4. Displays, plasma screens offer high-quality visual displays. 4. These applications leverage the reactive, energetic, and versatile nature of plasma to perform tasks that other technologies cannot, making plasma an integral part of modern technological advancements. Nuclear fusion reactors face a myriad of technical and scientific complications. Here's a detailed look at some of the key challenges. Plasma confinement. Maintaining the stability of plasma is difficult due to its tendency to develop instabilities, which can lead to disrupt ions. 1. The plasma must be confined for long periods at high temperatures and pressures to achieve sustained fusion reactions. 1. Material challenges. The reactor walls are subjected to extreme thermal and neutron loads, which can degrade materials over time. 1. Developing materials that can withstand the harsh environment inside the reactor, including the intense neutron bombardment, is a significant challenge. 1. Energy input versus output. Achieving a net energy gain, where the energy produced by fusion exceeds the energy required to sustain the reaction, is still a hurdle. 1. The current technology requires significant energy input to heat and confine the plasma, which can exceed the energy output. 1. Technological complexity. Fusion reactors are complex systems that require precise control and monitoring of numerous parameters. 1. The integration of various technologies, such as superconducting magnets and advanced diagnostics, adds to the complexity. 1. Neutron management. Neutrons produced in fusion reactions can activate the reactor materials, creating radioactive waste. 1. Designing systems to capture and utilize the energy from these neutrons is challenging. 1. Economic viability. The high cost of constructing and operating fusion reactors makes it difficult to compete with other energy sources. 1. Finding cost-effective solutions for the long-term operation of fusion reactors is essential for their commercial success. 1. Regulatory and safety issues. Establishing safety standards and regulatory frameworks for a new technology like fusion energy is complex. 1. Ensuring the safety of the reactor and the public is paramount, requiring rigorous testing and validation. 1. Public perception and support. Gaining public support for nuclear fusion can be challenging due to the association with nuclear fission and its related issues. 1. Educating the public about the benefits and safety of fusion energy is crucial for its acceptance. 1. These complications are the focus of ongoing research and development in the field of nuclear fusion. Addressing these challenges is essential for making fusion a practical and sustainable energy source for the future. The current status of nuclear fusion research is marked by significant progress and international collaboration. Here are some key points. ITER project. The International Thermonuclear Experimental Reactor (ITER) is a major international effort to build the world's largest tokamak and demonstrate the feasibility of fusion as a large-scale and carbon-free source of energy. 1. Advancements. ITER's construction is over 50% complete, with first experiments scheduled by 2025. It aims to produce about 500 megawatts of fusion power by the late 2030s. 1. Scientific breakthroughs. There have been recent breakthroughs, such as the 5-second pulse light-up in the jet reactor, which are considered major steps forward in fusion research. 2. Challenges. Despite the potential benefits, controlling thermonuclear fusion for energy production remains one of the most challenging areas of experimental physics today. 1. Future prospects. Scientists are optimistic about the prospects of replicating the Sun's energy source on Earth through fusion technology within the foreseeable future. 3. The fusion community is excited about these developments, as they bring us closer to realizing fusion power plants that can deliver energy to the electricity grid. However, there are still technological and scientific gaps to close before fusion can become a commercially viable energy source. 3. The role of organizations like the IAEA in fostering international collaboration is considered key to the success of fusion research. Controlling thermonuclear energy, particularly for the purpose of generating power in a fusion reactor, involves several key methods. Magnetic confinement. Fusion magnetic confinement. The most common approach is using magnetic fields to confine the plasma in a configuration that allows for sustained fusion reactions. The Tokamak and Stellarator are examples of devices that use magnetic confinement. 1. Inertial confinement. Fusion inertial confinement. This method uses lasers or ion beams to compress a small pellet of fusion fuel to achieve the necessary conditions for fusion. The rapid compression heats the fuel to fusion temperatures and the inertia of the fuel mass holds it together long enough for fusion to occur. 1. Gravitational confinement. While not applicable to man-made reactors, gravitational confinement is the natural process that occurs in stars, where gravity compresses the stellar core to temperatures and pressures sufficient for fusion. 1. Inertial electrostatic confinement. Electrostatic confinement. This technique uses electric fields to confine a plasma. An example is the fusor, which uses an electric field to accelerate ions into a central region where fusion can occur. 1. Temperature and pressure. Fusion requires extremely high temperatures, on the order of 100 million degrees Celsius, to overcome the Coulomb barrier, the electrostatic repulsion between the positively charged nuclei. High pressure is also needed to increase the likelihood of collisions that can lead to fusion too. Plasma heating. Various methods are used to heat the plasma to the required temperatures, including ohmic heating, passing a current through the plasma, neutral beam injection, and radiofrequency heating too. Plasma stability. Maintaining plasma stability is crucial to prevent energy loss and achieve a net energy gain. This involves controlling instabilities and turbulence within the plasma. 1. Energy capture. Once fusion occurs, the energy released, primarily in the form of fast neutrons, must be captured and converted into usable energy, typically by heating a fluid to drive turbines and generate electricity too. Nuclear fuel cycle management. Managing the fuel cycle, particularly for reactors using deuterium-tritium fuel, involves handling and recycling the tritium, which is radioactive and must be bred within the reactor from lithium-1. Materials science. Developing materials that can withstand the intense neutron bombardment and high temperatures inside a fusion reactor is a significant challenge that must be addressed to control thermonuclear energy. 1. These methods and considerations form the basis of ongoing research and development efforts in the field of nuclear fusion. The goal is to create a controlled environment where fusion can be sustained and harnessed for energy production, ultimately leading to a potential source of clean and virtually limitless power. However, significant scientific and engineering challenges remain before this vision can be realized. That was all. Goodbye.